So in this picture, there's like several different boundary layers that you can't see, but they're there. So there's the boundary layer over the wing of the airplane flying. The airplane itself actually is traveling in a boundary layer called the atmospheric boundary layer, which is the boundary layer formed by flow around the Earth's surface. So when people refer to turbulence on an airplane, it's because the fluctuations, like in the video, if you remember the video we saw last lecture, a turbulent boundary layer has lots of fluctuations and stuff. The fluctuations in the atmospheric boundary layer produce the turbulence that moves the airplane around. So those fluctuations are actually at a very large scale, versus the fluctuations and motions in the turbulent boundary layer over the airplane wing are very small. So they're not the same scale as the aircraft. Just a review of what we covered last lecture. So boundary layers are a viscous phenomena, and they form because of the no-slip condition on a wall. They they form because the no-slip condition causes fluid parcels to stick to the wall, and those fluid parcels encounter a shear stress then that is transferred through the rest of the fluid. So it creates the drag uh, due to viscous shear stress. There's two types of boundary layers, laminar and turbulent boundary layers. Laminar boundary layers they have low wall shear stress and they're smooth. Like they're called laminar because they're laminar flow, which is usually smooth. Turbulent boundary layers have a high wall shear stress, lots of mixing. The video last lecture that we saw was a turbulent boundary layer. So it's a very complicated flow phenomena. We can characterize boundary layers by a local Reynolds number. It's called local because this varies at different points along the boundary layer because of X. So for a smooth flat plate, which is a very special case that we'll look at in this course, we know roughly the Reynolds number where the laminar boundary layer ends. And we also know the Reynolds number where the turbulent boundary layer starts. So that's 100,000 and 3 million respectively. So in between there is a transition region, which we're not really going to worry about. The reason that we're looking at such a specific case um, is that, yeah, boundary layers are really complicated. So in reality, if you're doing anything that involves drag on a boundary layer, you probably have to characterize that using experiments or CFD. So we're just studying this because we have kind of some nice numbers and a nice geometry that we can look at. We can understand then the physics of boundary layers. Speaking of the physics of boundary layers, so we have those expressions for the boundary layer thickness, delta x. And again, we define that thickness based on the height where you get 99% of your free stream velocity. So velocity basically is zero at the wall, and then it slowly recovers up to the edge of the boundary layer. And when it's at 99% the free stream velocity, we say that that's the edge. So we have an expression for that and for the skin friction coefficient for laminar and turbulent boundary layers on a smooth, flat plate. So this allows us to compute, basically the thickness for this very special case. In general, you'll need different expressions that you might get, I guess, from CFD or experiments, or I guess in some cases this might be in a code book or something like that for boundary layer thickness, skin friction coefficient. Context again, we're going to talk about boundary layers. Next week, we're going to finish off module 2, I think. So we'll talk about acceleration, volumetric strain, and put that all together and kind of finish writing Newton's second law for a fluid. So today, we're going to, like I said, continue talking about boundary layers. So I'm going to illustrate the effect of changing the different parameters. You remember I mentioned how boundary layer thickness varies with Reynolds number, and what that means for free stream velocity means thinner boundary layer and so on. So I have kind of an interactive thing that is going to allow us to visualize that better. I'm going to explain why the turbulent boundary layer has a higher wall shear stress. I'm going to give you a formula to compute the drag force on a flat plate. And we're going to look at some cool applications of boundary layer theory in real mechanical design problems. Are there any questions before I start? Yep. So let's start by looking at the effect of Reynolds number, because I had a lot of questions after class, and I know it's confusing and unintuitive. So a lot of fluid mechanics is like that. So we can spend a little bit of extra time at the beginning here talking about that Reynolds number. So let's recall the effect. Of that Reynolds number. That's defined like this, rho u infinity x over mu. So we're going to have two scenarios. Okay, let's pretend that we're at a fixed x. So we're somewhere along our flat plate, and we're going to stay there. In that case, a higher Reynolds number means a thinner boundary layer. So that Reynolds number is the Reynolds number here. We talked about different ways we have to change that Reynolds number. So what that produces means if we have a fluid with a higher density, we get a thinner boundary layer because the density is proportional to the Reynolds number. It means if we have a higher free stream velocity, we get a thinner boundary layer. So I'm doing equals and then just quotes. So these are all the cases that produce a thinner boundary layer, and the inverse is also true. And if we lower the viscosity, we also get a thinner boundary layer. So this isn't, I guess, apparent from the Reynolds number of x equation. This is just kind of the rough physical properties that we can intuit about a boundary layer. Any questions about those relations? So this is for a fixed x location, how our free stream properties vary the thickness of a boundary layer. Okay, so let's now fix our free stream properties. So fix rho, u infinity, and mu. In that case, the boundary layer gets thicker as we move along x. So thickness grows along x, which is the behavior exactly which we saw last lecture. So say we have x here along our plate. The y-axis is delta of x, where delta is the boundary layer thickness. The boundary layer thickness will grow along x like that. Depending on whether or not the boundary layer is laminar turbulent, we can compute that thickness for a given x using the expressions I gave last class. Okay, so any questions about that? Yes, please.
I may be getting something wrong, but if with a higher x, our Reynolds number increases, right?
Yep.
But in our equations you gave us boundary layer thickness, the thickness depends, say in the laminar case, or it's proportional to 1 over the square root of r squared, so our Reynolds number squared, square root. So when the Reynolds number increases, should the boundary layer thickness decrease?
Yeah, it's a good question. Let me just kind of repeat the question. I'll get the actual expression out here just to clarify. Yeah, so the question is, I'm going to write this down, but then I'll erase it. It's a really good question, so that's why I'm going to repeat it. So for a laminar boundary layer, we have delta of x is 4.91 x over the square root of the Reynolds number. So if you look at this, you say, well, as the Reynolds number goes up along this plate, so in the x direction, you can think of this as x or REX. So as you go along the x direction for fixed free stream properties, your Reynolds number will increase. So you say, doesn't that mean delta x decreases? Because delta x, looking at that equation, would be 1 over the square root of Reynolds number. So the Reynolds number of x is, if you expand this out, so you get 4.91 x over the square root of rho u infinity x over mu. So there's actually an x on the numerator. So this is not the, this is the case here for a fixed x. or for a changing x, like when you fix the free stream properties and you move along the boundary layer, delta of x is actually proportional to the square root of x because we have an x here and here, right? So yeah, really good question. Does that answer your question? Yeah. Okay. So that's why we get that curve that kind of looks like 1 over the square root of x. Any questions about that? Okay. Actually, I'll leave that. It's not bad. Yeah. So I'm gonna do this. I'm gonna try and do this demo here now. So this is a. If you're curious about doing kind of a web browser-based fluid simulation, this is in the fluid dynamics study break section on your Learn. So what this is it's a CFD simulation that can run in your web browser. So it's a very inexpensive one and it can run in real time. So I've drawn here the boundary layer on a flat plate. So what this is colored by right now is the x component of our velocity vector. So it's kind of colored by ux. And this black line is our flat plate. So the coloring out in the free stream, that dark red is kind of the free stream velocity. And the boundary layer is the colored region here, right? So this simulation allows us to adjust the flow speed and the viscosity. So we have these like sliders down here that you can play with. So if I was to increase the flow speed, what do we expect to happen to the boundary layer thickness? It gets thinner, right? Okay, so I'm gonna do that now. Okay, so it started there. As I increase the flow speed, the boundary layer gets thinner. See? I'm moving this slider down at the bottom. So with a slower flow speed, we have a thicker boundary layer. This simulation also allows us to adjust the viscosity. Now viscosity is on the bottom of the Reynolds number. So what do we expect as I raise the viscosity? What will happen to the boundary layer thickness? It gets thicker, right? This makes sense. Like if you have a really thick fluid, you expect a big region of kind of viscous flow near the boundary. So if I raise that, hopefully you can see that the boundary layer gets thicker as I increase mu. And as I decrease mu, the boundary layer also gets thinner. So if we have a really, really fast flow with a really low viscosity, we would expect like a very small boundary layer on this plate. So this is kind of a visualization that we can use to intuitively understand how our fluid properties, by the way, I'm varying the free stream properties here, affect the boundary layer. This is also interesting. So we can draw the tracers in the flow. I'm going to try maybe increase the contrast of the screen there. Yeah, so you can see the tracers. Hopefully you can see the tracers moving outside of the boundary layer and see how much faster they move than inside the boundary layer. So these like little gray things, kind of hard to see there, but see the ones on the plate? They almost stick directly to the plate. So they're just off the plate, which is why they're moving very slowly. And then throughout the boundary layer, the parcels will move at different velocities. So that velocity grows as you move away from the plate. Yes, please.
On this, is there a way to represent like the transition period for the boundary layer? Because I'm still not entirely sure what the transition region even is supposed to be.
So the transition region is a region where we don't have a fully turbulent boundary layer yet, and we don't have a laminar boundary layer. So laminar boundary layer, this is a laminar boundary layer actually, so it's very smooth. The transition region is when there might be like a fluctuation that happens, but then it's dissipated, and then like another fluctuation dissipated. Whereas the turbulent one, the fluctuations are just continuously happening. So yeah, don't worry too much about the transitional one. So this is a laminar. The turbulent flow is much more expensive to solve numerically than laminar flow. So this is basically a laminar solver, but it can still like show us the boundary layer. Yes, please.
So in the limit of distance the boundary layer goes to 0, is that actually an effect of parcels like an individual particle itself, or is that just like a macroscopic like equivalent? So like if you actually had a particle, does it just go to like the surface and then it stops and kind of like chills out for a second, leaves and then goes to a different region? Or
So
like
what
does
was
it
the limit that
is there
you?
actually just a layer of like fluid particles that just stick to the surface?
I guess you said in the limit of which at the beginning of your question?
Distance
Oh, yeah. So in the limit of distance, there's the first parcel on the wall does stick to the wall, but that limit is very small. So like that's basically like a dx, like a we have a continuum. So the first parcel sticks to the wall.
It's like an actual,
In an actual flow? Yeah.
like a single, like H2O stick to the surface.
It's a really good question. So the question is like, do you actually get like, say you drag a plate through water, does the water now just always stick to that surface? It's complicated because for practical flows like that effect actually exists, and we can use that in our analysis. But when you get, say you drag something through water, and you say, okay, the water is going to stick to the surface, and you take it out of the water, the stuff on the surface is so small that like surface tension forces will cause it to roll off. Like different things, different interactions will happen. So that no slip condition, it's a real condition that happens. Like for example, if you're on an airplane and it's raining outside, even though the plane is flying at like hundreds of kilometers an hour, if you see the raindrops, they move like super slowly along, but they move super slowly. But like the ratio of the velocity that they're moving across the window to the plane speed is very high. So um, yeah, it does happen, but it's it's a very small effect. I mean, it affects very in a very small scale, but it produces like major forces that we have to account for. Any other questions? So yeah, if you want to play around it, this is just linked on Learn. So this this actually isn't really used to normally study boundary layers, but you can do different. You can look at different shapes in this and play around with see what flow looks like around some common shapes. We're going to use this, probably coming back to this a couple times in the course. So for example, like the flow we studied before in your first tutorial around a cylinder is like this. But at a certain point, I'm not sure if, depending on what the simulation is, we would expect some unsteady phenomena to happen here. If I can drag this, hold it. So this is all solved basically just running on my computer in the web browser. So this is a numerical simulation technique called the Lattice-Boltzmann method, and it can run very fast for laminar cases. So what happened there, actually, that was really interesting. So I'm going to reset the fluid. So this is what I was talking about sometimes about inducing turbulence. Let me make this a little bit more viscous and see if I can. So they have a thing called drag fluid here. So this is like almost perfectly symmetrical because it's a numerical simulation. So if I drag this and induce some sort of, it worked for the higher viscosity case. If I have this and I drag it and induce some sort of like motion in the flow, that motion will continue to be propagated. So you need a small disturbance, but once that disturbance happens, it keeps happening. So this eventually is like what leads to turbulence. Even though this is a laminar simulation, you can still get unsteadiness that happens. Okay. But anyways, that's kind of outside the scope of this lecture. This is a fun thing to play around with though, if you want to go and find that on Learn. Any other questions about that? Yep. Yep. Once the oscillation starts, like once the vortex shedding happens, it will just go on forever. It's a self like sustaining. There's no the energy input to that is just all coming from the free stream. So it's not like it's going to damp out or anything like that. So there's probably like some sort of energy balance that has to happen between the dissipation due to viscosity and the energy that wants to do that unstable motion. Okay, so talk now about shear stress within a boundary layer. So this is the wall shear stress expression for a Newtonian fluid. Okay. Let me draw a plot now of let's kind of look at the velocity profile at one fixed x location and compare if we assumed a laminar or turbulent boundary layer at that location, how the velocity profiles would differ. So the y-axis will be y and the x-axis will be u of y. Sorry, u of y. So the turbulent, I guess I'll do the laminar one first. So the laminar boundary layer kind of looks something like this. So this, what I'm drawing here is basically a velocity. You can imagine that as the velocity profile at a given x location. So that is the laminar case. Now the turbulent boundary layer should achieve the same kind of free stream. It goes up to u infinity outside the boundary layer. But what happens within the boundary layer is what produces the higher drag. So that's what the turbulent profile looks like. So now does someone have an idea, based on these profiles here, why a turbulent boundary layer would have a higher wall shear stress? So based on the equation we have here and the profiles that I've drawn, why would the turbulent boundary layer have a higher wall shear stress? Yep.
Like sheds, like big vortices, like I think that goes.
That produces this profile here. So the vortex shedding and the turbulence in the boundary layer causes like large scale, high speed regions to be sort of mixed downward. And it also causes like the low velocity near the surface to be mixed upwards. So it creates more drag. But in terms of, say, this equation and the profiles that I've drawn here, what's actually producing the higher wall shear stress? Yep, please.
Velocity gradient at the wall is much higher in the turbulent case.
Yes, exactly. Yeah, is that what you're going to say, Moo? Okay. So the reason is that the velocity gradient here, du dy wall, is very high for the turbulent case and less so for the laminar case. So the wall shear stress and the friction drag created on the surface, it depends on that instantaneous slope at the wall. So when I talked before about how it's probably $1 billion industry estimating this, this is why, because it's very expensive to resolve that boundary layer. So the computer simulations, I don't know if you've taken much in numerical methods and stuff, but regions of very high gradients, they require more basically discretization points to resolve those gradients. So this is basically the key problem in simulating turbulent flows, is that wall region. And in turbulent flows, the only way our kind of body interacts with the flow, all that happens instantaneously at the wall. So you need to get the wall right to get the rest of the flow right. But getting the wall right is very, very expensive. So that's one of, if not the main problem in simulating turbulent flows.
Doesn't that property change once you pass the intercept though? Because then the gradients are basically the same, but the turbulent one's higher.
Yeah, exactly. So for example, are you asking like say the shear stress here? Yeah, so that tells us that the shear stress in the fluid might be different. But the thing that creates the force on the wall is the shear stress at the wall. So the shear stress throughout our fluid is just mu du dy, the gradient. So say the fluid parcels here compared to the laminar boundary layer, the slope isn't as high. So you're right, they would experience like less shear. Any other questions about these profiles? So higher du dy at the wall. more skin friction drag in turbulent boundary layers. So this is actually a problem in a lot of industries. So if you have kind of a long, smooth surface that you're pulling through water, you want to try and make that surface, you want to try and get the boundary layer as laminar as possible, because as soon as you get that transition to turbulence, you get a higher wall shear stress and you need to add force in order to keep pulling it. So there's an article here about these computer simulations. People did some CFD studies of barnacles along ships. I'll get the lights off again. So a ship's hull is a very, very long, like smooth surface that has to get dragged through the water. So that basically you want to keep the flow as laminar as possible along that to keep the drag force on the hull as low as possible. So this is why they take, for example, like barnacles, and it's called biofouling. So like biological things attach themselves to the ship's hull. And the roughness of those things causes the boundary layer to transition earlier to turbulence. So like remember last lecture when I mentioned if you put a trip in a boundary layer, you can cause those turbulent fluctuations to happen earlier. That's basically what these barnacles do. So there's the article you can read through here. I think they said you can get up to 80% more drag with lots of barnacles on a ship's hull. So they have some pictures of the simulations that they were doing. Maybe let's do a pop quiz if you remember. So is this a sequential or diverging color map? Diverging. Yeah, I heard diverging. That's good. So it is a diverging color map. I'm not sure that it's the most appropriate choice of color map for this flow because the mapping goes from 0 to 0.15. So there's sort of an artificial line created at that, I don't know, 0.075 mark. I'm not sure if that's physically significant or not for this. If it's not, then they probably would have been better off using a sequential color map so you don't get that artificial gradient change. It does make things a little bit easier to see, but that might kind of be an artificial color gradient. So anyways, they have these small, like, I guess, I don't know how they modeled the barnacles. I don't know if they show that in here. Probably in their paper they explain how they modeled barnacles. And they simulate the flat plate with a bunch of different numbers of barnacles and density of barnacles and things like that to figure out how much more drag you get from these barnacles. And the reason that the drag is higher is because the boundary layer is more turbulent, so there's higher wall velocity gradients. So any questions on that concept? Okay. I should mention that the reason that this color map was probably used is it's actually the default color map in a lot of software. So if you don't change it, you're getting basically divergent. Not a big deal. Not a big deal. We can still very easily see that there's differences between the cases. Okay, so that's an example of how the higher skin friction drag in a turbulent boundary layer can be a bad thing. Let's try and compute the drag force along a boundary layer now. So let's say we have same situation. So we have flow coming in over a flat plate here. Okay. So the width of this plate is going to be W. Overall length is going to be L. We know by now that we get this boundary layer forming along the surface of this plate. It keeps growing. So I'll cut it off there, but it does, keep growing, as you know. So the delta X is the thickness of this. Boundary layer. We're going to consider a small, very small section of wall here with width dx. So that is dx long, where I'll do our coordinate system here. X and Y. So if we say, actually the coordinate system is defined in the flat plate relations using the front of the plate as 0. So it's defined from here. So Y and X. Okay. So the X location of this will just be X. Okay. So we're going to analyze basically the shear stress on this very small element. So there's a shear stress on this fluid, on the fluid elements at that location. And this is a 2D, the boundary layer relations I've given are for a 2D flow. So a 2D boundary layer. So it's the same along that entire W. You'll notice, like in the expressions I gave, there's no sort of Z into the page. That's because the derivation of those expressions require a 2D flow. So uniformity along that direction. So the dF, call this dF drag, is tau wall at that location X times dA. This expression here is just F is shear force is just the shear stress times the area over which the force happens. So that area I'm going to ask for help again. So what is this? See this blue shaded area that I'm highlighting? What is that area? WDX, exactly. Times. So it's just a rectangle with WDX. So we can now basically that's the dF drag on that very small surface. So if we integrate this along X, we'll get an expression for the force on this entire plate. Move this over. So F drag. What we're going to do as well, since we're in the 2D case, is we're going to compute the drag per unit width. So that's F drag over W. Integral of 0 to L. Tau wall of X dx. Okay. I'm going to pause here. So are there any questions about that integral, that integration? So W is a constant along X, so we can move it. So all we have to do is just integrate the wall shear stress along X. Okay. The expressions I gave last class were in terms of skin friction as a function of X, skin friction coefficient as a function of X. So in order to get wall shear stress, we have to multiply that skin friction coefficient by, based on the definition of the skin friction coefficient. So 1/2 rho U infinity squared So the skin friction coefficient is the wall shear stress divided by this quantity here. Now you have those skin friction coefficients in the notes from last lecture basically as a function of X. So you can integrate now, if I tell you there's a laminar boundary layer over this entire plate, then you can integrate that skin friction coefficient from 0 to L, and you'll get the expression for the drag force per unit width. I'm going to box this expression. Are there any questions on that integral? If you're confused about this integral, it's important you ask now because this will be on the homework and you'll probably see this in the tutorial next week as well. Any questions about this setup? Okay. So I will just summarize now the boundary layer notes that we're doing. So key points on boundary layers. Okay. First one is The boundary layer forms due to viscous forces plus the no-slip condition. So what would happen if we didn't have the no-slip condition and we just had a viscous fluid, but we didn't assume the no-slip condition? Let's assume that the fluid is just allowed to slip over the surface. The only viscous forces are created by relative motion between parcels. So if you don't assume that the fluid sticks to the wall, there's no viscous force being generated there. So you don't get boundary layers without the no-slip condition. Point two is there are two types. Laminar and turbulent. Big point is turbulent. Boundary layers are higher drag. Due to our larger velocity gradient. The next point is we predict which type of boundary layer we have. So we predict which type of boundary layer forms using the Reynolds number. And it's not just the Reynolds number, it's the Reynolds number plus some value of the Reynolds number that we think it's going to become laminar, we think it's going to become turbulent. So for a smooth flat plate, Reynolds number less than 10 to the 5 means we're laminar. If it's greater than 3 million, it's turbulent. Yeah, again, we're just looking at the very special case of smooth flat plate where that transition happens. But in general, this is much more complicated than this to just predict the transition of a boundary layer. In fact, if you've ever come across CFD of a turbulent flow, a lot of the times it's just assumed all the time to be fully turbulent. So for some flows, that leads to inaccuracies. The last point is integrating. So the skin friction coefficient is like a non-dimensional wall shear stress. If you know your free stream properties, you can calculate what that wall shear stress is. So that's the local wall shear stress. Local meaning it's at a point X. And if we integrate that along the plate, for total drag. That's kind of a summary of this boundary layer topic. So are there any questions about any of those comments? Okay. So we're going to talk about now just total aerodynamic drag. So let's talk about pressure drag and skin friction drag. I'm just going to briefly touch on this because there's a lot of actually interesting applications of boundary layers, but to look at them, we have to study in general aerodynamic drag. So the total drag on something is usually, so total drag is usually pressure drag plus skin friction drag. Skin friction drag is exactly what we saw above. It's the sum of the wall shear stress over the surface. Pressure drag, we've seen before how to compute forces due to pressure on something. That's what pressure drag is. So the drag is usually kind of in the x direction. It's along the flow. So like the drag on the airplane is in the same direction as the velocity of the airplane, for example, and the lift is up. So pressure drag, say you have like small surface element. Again, this isn't that big of a deal in this course, but there's some interesting applications if we understand this. So the pressure drag is produced by this, say this normal force, and the skin friction drag is produced by this tangential force. And that tangential force, the skin friction drag, depends on the near wall velocity gradients, and etc., like we just looked at. So smooth bodies with small frontal area the drag force on that body is going to be dominated by skin friction. So for example, the flat plate that we've been studying in the last couple lectures. If you put a flat plate in a wind tunnel, the drag force is mostly that skin friction drag. So it's the integration of the drag, the tangential surface. It's the integral of the tangential force, which is caused by that velocity gradient near the wall. But for bluff bodies, with a larger frontal area, those are dominated by pressure drag. So for example, we have a cube. This is a bluff body. It's not very smooth, and it has a large frontal area. So the flow kind of comes over and it rolls behind it. So the frontal area I'm talking about is this area that the flow sees when it's coming at it. So the aerodynamics of this body is dominated by basically pressure drag. Sometimes it is worth it to induce a turbulent boundary layer to reduce pressure drag. So how could, we haven't really covered this, so the reason that a turbulent boundary layer can reduce pressure drag is because it causes the flow to remain attached to the surface. So the reason is that a turbulent boundary layer can delay flow separation. Now flow separation, I'll play a video just so you can see what that is. It's when the boundary layer separates from the surface. So this boundary layer isn't always attached to the surface. In certain cases, the boundary layer will become unattached to the surface, and that the pressure drag increases a lot when the boundary layer separates. So flow separation, meaning boundary layer separation, means high pressure drag. So I'm going to give some examples now of this concept. Okay, so let me just summarize before I go to the videos. So if you have two components of drag, pressure drag and skin friction drag, when the boundary layer separates, you get a lot more pressure drag. So you want to keep the boundary layer attached. And turbulent boundary layers tend to remain attached more than laminar boundary layers. So sometimes it's worth increasing your skin friction drag by activating a turbulent boundary layer in order to keep the flow attached. So there are lots of examples of this in practice. So I'll show what I mean by the flow being attached now. So if you've heard of airfoil stalling or a plane stalling, that occurs when the flow becomes unattached. So right now this flow is attached to the surface of the airfoil. We have a boundary layer over the surface of this airfoil, and as that angle increases, there's going to be a point where that boundary layer separates. And you'll see when there's massive separation of the boundary layer, the flow changes quite a bit, and this has a lot more drag. So this is a lot more drag. And it's mostly pressure drag. I'm going to turn off lights soon. So that's what airfoil stalling looks like. So there are certain times where you want to actually make this boundary layer more turbulent to delay stall. So if the boundary layer is more turbulent, it tends to remain attached longer. So there's this guy on YouTube that put these things called vortex generators on his plane. So vortex generators are things you place near the leading edge of the wing, and they create turbulence in the boundary layer, so the flow doesn't stall as much. So I think he shows
58.
this guy put this stuff on his plane, and he put these strings called tufts on the wing, and they show us when the flow is stalling, the tufts will sort of go everywhere because the flow is pulling them everywhere. But when the flow is attached, the tufts kind of like press to the surface.
The game is over.
So see, it's attached over most of the wing, and it's kind of stalling over as the flow it's attached here, and then as it hits this edge here, the flow kind of separates, and that's why the tufts are all wiggly over there. So in comparison now, so these very, very small things on the surface, those are vortex generators, and they create a more turbulent boundary layer. So he's going to, okay.
55.
So he put vortex generators, let me go full screen. He put vortex generators along the outer edge of the wing. So there's only vortex generators on that half of the wing, and the rest of this is no vortex generators. So this is all fully stalled out here. There's vortex generators out there, so the flow is actually attached. So increasing the turbulence in the boundary layer has caused the flow to remain more attached. So this is good because the control surface of the plane is out there. And if your control surface of your plane is in a stalled region, it can't actually do anything on the fluid. So this can lead to loss of control. It's actually quite a serious issue. So that's one way to do it. There's a cool video by Red Bull Air Racing here. He's going to talk about this, but this is also the reason that golf balls have dimples. So the golf ball is kind of a bluff body with a big wake, lots of pressure drag. So the dimples, they're like little almost roughness in the surface, and they cause the turbulent boundary layer, and that kind of keeps the flow more attached over the back of the golf ball. So that's why golf balls are.
Hello and welcome to Tech Talk. I'm Jim Reed. In this episode, we're going to discuss a way you can increase the stall angle of your race plane and decrease the stall speed. Vortex generators.
Oh, look, there's a little wing rock.
So
That's
see how
called a
small they
stall.
are? Like the ones that they're
Vortex
using are
generators.
those little rough sections. That's all you need to basically trip.
Oh, look, there's a little wing rock, and that's called a stall.
To understand how vortex
I'll post this in case you want to watch it.
laminar
It
boundary
explains like different laminar and turbulent boundary layers. I think
example of this principle is a golf ball. The dimples on the surface of the golf ball are vortex generators. They create a turbulent flow on the ball, which is more drag than the laminar flow, but it's far less drag than separated flow. This allows the ball to fly much further in the air.
so on a plane in a normal cruise condition, you don't want really that many vortex generators because you're getting higher skin friction drag. So your plane has more drag on it. But it helps with planes that do stunt flying like this. You don't really care that much about like your fuel efficiency in your normal cruise. You just want to be able to like fly at really high angles of attack without stalling the plane. So it's worth it in that case to add a little bit more skin friction drag to keep the flow attached and dramatically reduce the overall drag. So most airplane wings, there's some cases of commercial airliners where they'll put this on there, but for the most part, you don't see this on commercial airliners. Any questions about that? I'm going to post these videos on the Learn, so if you're curious to watch the full ones, you can. Yeah, you have a question? Yep. Any other questions? No? Okay. Thanks, everyone. Have a good weekend.